All right, before we get into shell, let's just kind of recap what we've been talking about. When we talked about the disk method, the area shaded butted up against the x-axis. For example, this little thing right here. And it's kind of hard to tell because it's kind of a small print here. But this would be the x-axis, and so this would be our shaded area. Everything's butting up right against the x-axis. Well, in a second I'm going to show the animation, and the resulting three-dimensional figure is this little sideways vase. Here's an example of the washer method. In which there's a hole caused by the gap of the figure, which is not butting up against the x-axis. Here's a gallery of some of the figures made by the disk method. For example, here is a x squared. It's a parabola. So if you look here closely, that would be the shape of a parabola. And it would butt up right against the x-axis. And this would be the resulting three-dimensional figure. This is the square root function. So if this is the origin right here, it would kind of curve out. This is the resulting figure using the sine x. This is just a polynomial function. And then, of course, these are some more intense exponential or trig functions. But let's just kind of take a look at a couple of them and see how they're made using the disk method. How about we take a look at the polynomial one? So they're just kind of cutting it into little strips, and then they would take those little strips and they would make these little circular disc, or the volume of all of these discs right next to each other. It creates a three-dimensional figure, which you'll see in just a second. And again, you can see the shaded area would butt up right against the x-axis here. And then, of course, the reason why these are thicker is because the distance from the center line up is longer, and hence it has to be a reflection of it underneath here. So you get the idea there of the disc. Let's go to our washer. So let's take a look at this region. You can tell closely that there's some white gap here. There's white gap here. Obviously a gap right here. So these are all just examples. And again, if you look at the screen right next to them, this is how you're partitioning that purple area. And then you would take all of those partitions with that opened gap in between, and it creates a hole inside. Thus, that's why they get the name washer. Again, this is the washer method because there's a gap at some point. Not all of the area is butting up against the x-axis. And now let's get into the shell method. Now the difference between the washer and the disc was that the disc butted up against the x-axis. The washer, we revolved around the x-axis, but there might have been some white gap in between where the area was shaded and the actual x-axis began. But everything revolved around the x-axis, which happened to be a horizontal line. So now we're going to talk about the shell, which is revolving things vertically, so sideways. So here's an original region. So obviously we could look at this as a disk if we were revolving around the x-axis, but we're not. We're going to revolve around the y-axis, sideways. All right, let's take a look at another one. An upside down parabola rotated sideways around the y-axis this time. Kind of looks like a bundt cake, if you know what a bundt cake is, if your parent or guardian's ever made you a bundt cake. But if you notice, all the ones that we've shown you so far has this area shaded that goes right up against the x-axis. Even though we're not revolving around the x-axis, the colored area is butting up against the x-axis. So let's look at some that are actually the combination between two graphs for this one or this one. Let's look at this one. Again, we're doing the shell method because we're going sideways. So your learning target is that students will be able to find the volume of a solid of revolution made by revolving a region around a line using what we call the shell method. Okay, so all of the methods that we've been discussing so far on how to find volume have always had a revolution line being the x-axis or some other horizontal line. So we are going to transition in a few minutes into revolving around the y-axis or a vertical line. So let's start with this function right here. Okay, an upside down parabola, which is also signified right here. So what we're going to do now is we're going to revolve it around this line right here, which we call x equals -1. So we are going to be turning this sideways, and in the process of doing that, because there's this gap here between the function ending and the axis of revolution line, we're going to create a hole kind of inside the function. So then this is what it actually looks like. You're going to go around sideways, but because again there's a gap there, there's this like cylindrical hole. So we're going to call this the shell method. Okay, so you've seen examples of the shell method in an animation. So let's talk about how we're going to use the shell method with our problems. Remember that it's most effective for a vertical axis of revolution, namely the y-axis, but sometimes it may be a different vertical axis of revolution. In that case, it may just be in the equation form of x equals some number. So it could be over here, it could be over here, it just depends on the problem. Now, just a reminder, when it says the volume of a shell, think of the shell as being like the outer coating of a Skittle. So you've got the candy on the inside, and then you've got this really thin layer coating on the outside. So that's what we're trying to find the volume of. So what we're going to do is we're going to have a function here, and we're just going to partition it into this little rectangular piece here. And our formula says volume is equal to 2 pi from a to b, and a to b are still our x values of integration. And then it has this p of x times this h of x. So it's pretty much like the radius times height idea. However, the radius is really going to be, you have to envision this now, it's kind of hard to see on this two-dimensional graph here. You're going to try and envision something going sideways. And what is the distance from this axis of revolution to the center of this little partition I made? So if it's revolving around the y-axis, that will always be x. It's the distance, some kind of partition. We don't really know what it is, but the distance from this y-axis to our center of our partition. And then the height, well, the height, how tall is it? It's always that top function minus the bottom function, like we did back in the very beginning of this chapter. Now, what happens, though, if we change our axis of revolution to something way out here, or even in here? So that means, what that means is that the distance from your axis of revolution to your center part is going to change. For example, if I have this graph going on, and I want you to revolve around this line x equals 2. Well, right now, this distance is 2, but as I partition gets further and further, either closer or away from this axis of revolution, right now I would say it's at 2, but as this gets closer to the axis of revolution, it may be 2 minus a number. What that number is, we have no idea because it's a variable. So what we're going to do is, if the axis of revolution is not the y-axis, this x becomes the axis of revolution minus x, and then the rest will stay the same. Refer to your note card that I had you make earlier at the beginning of this chapter back in the second trimester.